Hello everybody, and welcome to my video on confidence intervals for the proportion. Obviously, that pertains to this third formula. And now, since this is our third formula, and you've watched the videos for the first two, you kind of have an idea of how I attack these problems. But just in case, let's be very clear. When we're building a confidence interval, how does one do it? Well, let us take a look at a few examples. For example, 1. A recent study by New Yorkers state that in a sample of 2,000, the percent who support Governor Cuomo is now 35%. Build the 90% CI for the true percentage of all New Yorkers that support Governor Cuomo. Well, it's very important to me that hopefully this sample was done representative and random, so that way I can take the data in the sample and push it to the larger crowd utilizing confidence intervals. So what are my steps in building a confidence interval? The first is truly understanding which confidence interval you want. So let's read this question carefully. Build the 90% confidence interval for the true percentage of New Yorkers. That's why I know which formula I want. And that is the P plus or minus Z times radical P times 1 minus P over N. This is our confidence interval we want for this example 1. And that really is my first step. Pick my right formula. And there it is. Now, the good news is there is no 50-50 gamble here. The confidence interval for proportion is this one. All right, now, step 2. Get all the information you need, P, N, and Z. Get all 3 variables. Because once you have all 3 variables, then you can build the margin of error. What is the margin of error, you ask? Well, my friends, the margin of error is this backhand. It always is the backhand. See, what you do is you take your point estimate, your estimate for where you believe the true population percentage is, and plus or minus a little error, and that creates your confidence interval. And so that's why in stage 4, we're going to have a lower bound and an upper bound. And so that's how we go about building a confidence interval. So, all right, let's talk about these letters P, N, and Z. How does one get to them? Well, again, let me go back to the formula. I would pause the video here. I would take a picture of this so you see the formulas I'm working with. This is the one I want because it's confidence interval for the proportion. If I wanted one of these, I'd read and make sure it was for the mean. This is confidence interval for the proportion in which I'm building. Got it. Are there other ones? Of course. I'm working with this one today. So what do we have here? I need to build the 90%, and just for giggles, I'll show you how quickly I can build the top 95% at the same time. What I need, though, are 3 things: N, P, Z. Then I can build the margin of error, and then I can build the lower bound and the upper bound, and we are good. All right, so what is N? N is always the sample size. Well, look at it. We sampled 2,000 New Yorkers. Got it. Sample size. What is P? Well, you got to know the definition of P. P is the sample percentage, all right? This is a sample percentage. So to find the sample percent, you got to understand your question. My question is, how many New Yorkers out of 2,000 approve of Cuomo? The good news, they've already done the math for us, 35%. Please, when you're utilizing Excel and or the formulas, you must move your number to a decimal. I hope you understand that 35% is 0.35. So if you're realizing something, going back to my piece here, I got 2,000. And this is 0.35. Awesome. All we need now is to find Z. Well, recall from previous videos, to find Z, you use norm S dot inverse. Now, how does norm S inverse work one more time? Well, think about your confidence interval. It is a 2-bar confidence interval. 90% is in between the 2 bars. So how much area is below each bar, or above or below each bar? That would be 5%. Because if you go 5, 90, and 5, that makes 100%. which means the area below the biggest bar, the tallest bar, would be 0.95. And that's what I'm putting in here to find my appropriate Z value. Let me go to a picture to make sure this is clear one more time. If I want to find the Z value, you got to give me how much confidence you want. You want 90% confidence. Got it. This is the Z value that will bound the 90% confidence. By symmetry, they're the same number. The Z curve is symmetric. So negative Z and Z will bound the middle 90%. How does one find the Z value that I'm utilizing? Well, if you understand Excel, Excel says give me the whole area below, and I'll utilize the calculus to find that Z value. If you give me that whole area, I will find that Z value. Well, that whole area is not just 90. It's got a little tail here, and that green is 5%, because this green is 5%. Both greens are 5% due to symmetry. If you take the middle 90 and the two outlying 5s, you get 100% of the picture. Hence, if I'm looking for how much is below this bar, that would be 95% area. And that's why I dump that into Excel, because norm S inverse always wants area below. Let's do it again. In this case, norm.S inverse. And at each time, I would pause the video, write down the code. Make sure you know the code. That's very important. When you're utilizing Excel, I'd have a little cheat sheet of common Excel codes that you use, like norm S inverse, T dot inverse. Know what they do, know when to use them. When you build a confidence interval, it's always norm S inverse, period. All right, when you're using the Z for confidence intervals, that's a good golden rule. It's always norm S inverse. And you just need to know you're looking for that top area down. So for 95%, you know you have a left and a right though, and that's 2.5 each. So I'm really going to plug in 0.975. This is the hardest, honestly, to me, the hardest thing to understand. Understand why it's 975. And that's because if you have 95% in the middle, 2.5 for each tail, that means below that top bar is 97.5. And there is our 196. Many of us have come to memorize for when you're building a 95% confidence interval, it's always 196. And that's true. It is always that, because the Z curve, there's only one Z curve, and 95% is the most predominant confidence interval we build. Excellent. Once you have those three things, we just plug and chug. We just plug and chug, my friends. All right? The margin of error is the back half of the formula. So I'm just going to dump that in using the formula. So it's equal to Z times, and we got to be careful here. It is the square root. Now, in the numerator of the square root, we have P times parentheses 1 minus P. Close that parentheses off, close off the other one, and divide that by N. Then I'll use enter. I'll go back up and I'll let you pause the video and see what I have written. All right, thank you for checking my work. It's always good to check the work. So the good thing is once you've written a code right, you can copy it by using the bottom arrow to copy that formula over. And you can check to make sure it makes sense for, again, the new column of data if you don't trust the copying. I always do this, especially if you're planning to produce these for a PowerPoint. So what do we have here? The margin of error at 90% is 1.7%. The margin of error at 95% is 2.1 or 2.09%. Notice, and again, it makes sense, as confidence goes up, margin of error goes up. And that's because as confidence goes up, your Z value goes up. And if your Z value goes up, your margin of error goes up. All right, now that you have the margin of error, you just have to understand how to build every single confidence interval. It is the point estimate. That is, where do you think the center of the interval should be? Well, if I really did do a really good sample and really did a good job of getting a representative sample, my number for the true percent of people that believe in or support Cuomo is somewhere dang near 35%. So using 35% as the center makes sense. But of course, I picked a sample, so there's some leeway, and that leeway comes in the error. And for the lower bound, we subtract off that error. On the other side, we take the sample percent and add on the error. In Boom Shakalaka, there is my 90% confidence interval that example 1 is asking for. I truly believe with 90% confident that the true percentage of people that support Cuomo is somewhere between 33% and 36.75%. Awesome. Why would you care about that? Maybe there's an electability measure. That is, he would need at least 40% approval to be reelected. According to my confidence interval, 90% chance he's not getting reelected. Got it. All right, let's continue over here. The cool thing, once you've written everything right once, you can just copy the formulas over. And now look, now you can say, well, wait a minute. If I increase the confidence, does it include 40%? The answer is still no. So even at 95% confidence, I don't believe Cuomo will get reelected if the only thing we worried about is if he got to 40%. We all know that's not true. That's not how politics works, okay? So in my example, I'm just caring about how do you build a confidence interval? And that's how you build it. How do you build a 95%? This is how you build it. What does the 95% confidence say? It says, I have 90% confidence that the true percentage of New Yorkers who support Cuomo is between 32.9 and 37.1%. What you do with that information, that's up to you. I can state the answer, though. Again, I am 95%. I am doing the other one. I know the question was for 90. I decided to go big time. I'm 95% confident that the true population percent who support Governor Cuomo is between 32.9% and 37.1%. What you do with that information, that's up to you. Is that a good ranking? I don't know. I would have to know what has been his typical ranking. Is it up? Is it low? I don't know. This is just a sample. Without having more information, I really don't know what to utilize this for. If there was a question that stated if he doesn't get to 40%, he won't get reelected, what do you think about his chances of getting reelected? I think his chances are very slim. Because again, I'm stating I'm 95% confident this is his favorability rating. And if you want him to get to 40%, it ain't happening without something huge, without something big. He is not going to get reelected, or without some kind of quote unquote sneakiness happening. Okay? And I'm not going to go down there. This is left for those people dealing with ethics, political science, so on and so forth. The great thing about statistics, it goes into all areas of life. All right? All areas of life utilize statistics. Cool. First, you got to know how to build the confidence interval, though. Once you know how to build the confidence interval, then we can get into the real life. What do we need to do with it? What does it give us? All right, guys, pause the video and attack example 2. All right, we're back. Example 2. Let's check it out. A recent study of workplace habits stated that in a sample of 248 workers, 190 would choose a more flexible schedule for a small pay cut. So I can imagine this study being done, and your task as a marketing or a management expert is to come up with a confidence interval on then, if this is what you did for the small workforce, imagine you did this for Walmart, who has thousands of workers. You picked 248 random workers, and 190 said they would choose flexible schedule for a small pay cut. Got it. Could you then build a 95% confidence interval for the true percentage? The answer is, of course. The key thing behind all of these things, of course, is you've done a nice random representative sample. To understand what those are, you really have to go into building studies, understanding how to build a proper study, design matrices. Okay, I copied down the formulas down to here because you can just highlight what you want, copy and paste. The great thing is once you've written it properly in Excel, it really is just a matter of retyping things, and it's quick and dirty. I want to get back to that. I did notice I forgot something, and it's not really forgot, but for example 1 and example 2, To build both of these confidence intervals, I am using the Z distribution. To utilize the Z distribution, you need to make sure you're allowed to use the Z distribution. So you should always check your assumptions. And what are your assumptions in this distribution? Well, besides random and representative, and that comes to the person building the sample, please make sure you've done it randomly, representatively. Look up what those words mean. Do not pick a biased sample. That will lead us to crappy conclusions and making us look bad. So random, representative, you got to do that. One thing I can check is, what are the checks for this distribution? Well, the check for this distribution, that is for this confidence interval, are slightly unique. All right, this is a confidence interval for proportion, and the checks for them come into two flavors. One, we need the number of yeses to be greater than or equal to 5, and we need the number of people, part B, that say no to my question to be greater than or equal to 5. Why? Take advanced grad school statistics. For us, we just learned the bounds are 5 and 5. 5 yes, 5 no. Then this distribution, we're allowed to use the Z due to the central limit theorem. The central limit theorem is awesome. And it pretty much states we can utilize the Z distribution, the normal distribution, as long as we satisfy a few rules. So going back to my formulas, I can use the Z distribution in an average confidence interval if n is greater than 30. That's what the central limit theorem says. Same thing down here for the T distribution. As long as n is greater than 30, we're roughly normal. So I am allowed to use Z and T. When it comes to proportion, I don't care about the sample size. What I do care about is I have enough people to say yes or no. That kicks my proportion into a very normal sample. And so that allows me to utilize the normal distribution. You're asking, well, wait a minute, what if I don't? What if I only have 4 in one of them? Well, my friends, you're in advanced binomial area, and that's not in this video. In this video, we're looking at greater than 5, greater than 5. Let's check it out, all right? 5 yeses. Let's go to the question. The question was, once again, 2,000 New Yorkers, and 35% agreed he did a good job. So 35% of 2,000, all right, off the top of my head, I believe that's 700, but let me just check. 2,000 times 35% is 700, and that's well over 5. We have well over 5 people, so awesome. And that, if that's the people that say no is 700, then obviously, yep, 1,300 are going to say no, because 700 and 1,300 make 2,000. And that's clearly greater than 5 also, and check a Rooney. So with a really quick check, I can see that I'm allowed to use the Z distribution. What I've written here is allowing me to utilize the normal distribution. In the formula, you have the Z. What gives you the right to use the Z distribution? This does. You see, if we don't have 5 above for both, 5 or more above in each category, yes and no, then we'd be stuck in the binomial distribution, working in confidence intervals with the binomial. Can be done. I'd prefer to use the Z distribution, the normal distribution. I can do that as long as we have the central limit theorem kicking in. So what I would do is, honestly, I'd take a formula sheet like this and put right next to it, when can I use it? For here, n is greater than or equal to 30. For here, n is greater than or equal to 30. For here, it's yeses are above 5, no's are above 5. And you got to understand what a yes is and a no is to really understand this distribution. By the way, if we already know the entire population is normal, then really I don't care about the sample size. I also got to add that caveat. There's really 2 things I can know here. If I know I'm sampling from something that's normally distributed, give me any sample size. If I have no clue about the distribution, then I got to have 30 to guarantee my normal. Same thing here. If you already know you're normally distributed, then any sample size would do. But if you're dealing with something nobody knows about, a top-end research that nobody knows about, you want to be safe and utilize 30. In fact, many researchers blow past that number to really guarantee the normality. They use 60, they use 120. You can look at other books, and people are really, see, 30 is that barrier. All right, you try not to be next to the barrier. So what do? You collect 60, you collect 90, you collect 120. How much do you collect? You utilize sample size theory. That'll be in my next formula to decide how many you should pick. All right, if you're curious how many I should pick to get a result, you would utilize these formulas below, but I don't want to get to those right now. This is a huge theory, and you really got to look at all of this together in a back-to-back lectures. 1, 2, 3, 4. And I've got videos on each one of these 4 topics. Putting them back to back, you really have a good idea of how to pick from your confidence intervals. And these are confidence intervals for a single stream of data. That's very important. If you have 2 streams of data and you're trying to compare them, you're not doing this. That's in my future videos. So you have a single stream of data. Again, to utilize this right here, you want n is greater than 30 unless you know about the distribution. If you already know it's normal, I don't care what sample size you have. And I would write those right there. Same thing here. I want n to be greater than 30 unless I know about the distribution of whatever we're doing here. Distribution of height, weight, IQ, GDP, in this case, whatever, not in this case, down here. I want 5 yes and 5 no. Yes would be the people that support Cuomo. No would be the people that do not support Cuomo. That's the first thing you should start with, is understanding you're dealing with a yes and no question. You're really dealing with a binomial type of distribution. But we're utilizing the Z because the central limit theorem kicks the binomial distribution into a normal distribution as long as we have enough people. And that's awesome with a capital A. All right. Sorry for that big rant. The cool thing is the actual calculating is so easy. The theory behind it, you just got to take time to let it sink in. And that's what I really try to preach. All right, so let's go here. Sample size, 248, right? That's how many people we sampled. And yes, I'm building both confidence intervals again, just for the fun of it. Notice, as I changed n, it changed the error, the lower bound, and the upper bound. Well, of course, these formulas are written perfectly, so I don't have to do them again. It's only the top 3 I'm going to adjust. So here we go. P. Please pause. Please see that P is not just freely given like example 1. P is easily found if you understand what the definition of P is. It's the sample percent. And the sample percent that would vote for Cuomo or support Cuomo is 190 out of 248. A whopping 76%. Same number here, 76%. Awesome. Norm is inverse, I'm not changing here. That's actually 90% and 95 still. So that's a cool thing. I can't state it enough. If the boss wants me to build a confidence interval, I build 2 of them quickly. And I ask the boss, which one do you want? I got you the 90, I got you the 95. Both say similar things, but if you want more confidence, it's got to be wider. It all depends on how much, bottom line, error do you want in your confidence. Are you okay with 5% error? Then we'll build this one. Are you okay with 4% error? You want a little tighter? You want a little tighter window? You want 90% confidence. I leave that up to the managers. All right. The most typical confidence interval is the 95, and here it is. So once again, I have the 95% confidence interval. I should check the yes and no's. Well, come on, right there it is. My number of yeses is 190. That's clearly over 5. And the opposite of 190, what would that be there? 58, right? 58 people said they would not choose a flexible schedule. So as a quick check, I see that I got above 5 on both ends, which means I can utilize the Z. Really, I need to make sure people understand statistics, why Z is allowed. And that's just a quick check. Some people just like writing it in, right? Some people like writing in the yes and the no. How many yeses do you have? I have 190 that would support. How many no's do you have? I have 248 minus 190. I have 58 people. Both of them are above 5, and so my checks are good. And that's awesome to have, all right? it's awesome to make sure we have the checks, because if your checks don't work, you're screwed. This whole confidence interval is garbage, and your statement will be garbage. What's my statement? I am 95, because that's what I wanted, 95% confident that the true population percent of people who would choose flexible scheduling over money is between, where's our low bound here? 95%. 71, turn it back to a percent now. 71.34% and 81.88%. Awesome. And there's my answer to part A. Part B is where we investigate what we built. Please notice, before B is to me the fun part. Why do we care about this? Why did we build it? There must be a reason we care about 71 to 81% would say, yeah, give me a flexible schedule over more money any days. Let me stay home 1 day a week and I'll take a slight little pay cut. Let me do that. So why would we do that? Well, part B, if the percent who support a flexible schedule is over 75%, the CEO would be willing to try this idea on a 3-year probational period. That's cool. The boss is ready. The boss is willing to do this. The team has, got the boss all hyped up about flexible scheduling and how this really will make the team happier, make the workforce happier, make it more efficient, more cost efficient. We got a lot of positive things. Part B. Can we make this happen? I'm pausing because I want you to think about the confidence interval and what it truly means if we're looking for over 75%. And my answer is simple. My answer is no. 75% is in the CI. And so that means there is a chance the lower bound is true. And if the lower bound is true, we don't have over 75% willing, right? The true percent in the workforce, without going to every one of them, and that's why you pick samples, is you do this so you do not have to ask every single person in the workforce, right? Walmart, thousands of employees. You don't want to have that time committed to that, unless it's some way easy to do it, all right? But so you don't. It is not an easy task to do, maybe. So in that time, you pick a representative sample of 248. Their opinions, if it's truly representative, should really be a nice idea of what the true, if I did for everybody. That's what this interval does, 71 to 88. 71 to 88 is really somewhere between those numbers with a 95% confidence. Somewhere between those two numbers is the true percent. If I surveyed every single person in the workplace, it's somewhere between 71 and 88. And that's the thing. Not 88, but 81, sorry. 71 and 81. I'm worried about that because that means it could be as low as 71.34%. All right? It could be as low as the lower bound, and I have no effing clue where it is. Excuse my language. I have no clue where it is. It could be 72%. It could be 73%. All of these numbers are less than 75%. So what I can tell the boss is, we're getting better. We're getting higher. But nope, we don't have a shot yet. We are clearly not over 75%. And that's very important. I'm waiting for that lower bound bottom line. I'm waiting for that lower bound to be above 75%. And then I can go to the boss and be happy. And it is not right now. What does it mean? It's time to bring out the marketing team. It's time to bring out the HR team and ask, why are people against it? What can we do to ease your pain so you'd vote more for it, right? We're not getting the percent we want. Let's go talk to them. Let's understand their concerns. Redo the survey and see if we changed anything. But first, we got to know how to build it before we can have all fun in the management marketing idea. First, you got to learn how to build a confidence interval. And if you follow my process, my code as you would call it, you could build a 99 and a 95 within seconds. Just break out your Excel. Know you need NP, and well, that's it, N and P, because Z is given. if you want 90 or 95. These are just given now. Margin of error, lower bound and upper bound, if you write the formula right, you never have to do it again. So really, just give me N and P, and voila, boom, 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 you're good. That's a cool thing. And if you needed the 99, build the third one. And then you can have all three for whoever needs it. You can do the 90, the 95, and the 99 and say, boom, which one do you want? That's how quickly I can build it, as long as you understand your technology. All right, guys, thank you so much for watching this video. Stay tuned for more.